Now, do you struggle with hypothesis testing? If yes, this video is for you. So this video is all about the basics of hypothesis testing, what it is, why you do it, and just some key terminology, no tough calculations. Now, the best way to explain this would be to just set up an example. Now, let's just say that the UK government has calculated that officially the chance of someone hitting a bullseye when they throw a dart is 10%. Now, me personally, I think I'm not too bad on a dartboard, right? I think I've got a better chance than 10% of getting a bullseye. Now, in me believing that I've got a bigger than 10% chance of getting a bullseye, I've offered an alternative belief. In other words, what you'd call an alternative hypothesis. There was a belief or a hypothesis from the government that everyone had a 10% chance of getting a bullseye. That's what you'd call a null hypothesis. I've offered my alternative hypothesis. So, who is right? Who is wrong, and how are we going to try and prove who is right or wrong? Now, the first thing that we need to establish is that we can't actually prove anything here. Now, we're starting to get a little philosophical right now about this, but you can't really prove that any kind of experimental event has a fixed probability. So the big rule number one with this, right? In a hypothesis test exam question, you are never proving hypotheses. You're never proving if this one is true and this one is false. Never use that word prove. You can't prove the fixed probability of a probabilistic event. You can't prove what that value is. But what you could do is you could get some darts, throw some darts at the dartboard, count how many bullseyes you get, and work out your success rate, so the percentage of times that you get the bullseye. Now, obviously, what you would do in theory is just throw the darts forever, infinitely many times. Obviously, we can't do that in reality, so what you do is you throw the darts for a fixed number of trials. Now, let's just say that we throw the dart 20 times. And I'll just write our hypotheses that we mentioned before, the H0, which was our null hypothesis, the H1, our alternative hypothesis. Now, before we even throw the dart 20 times, let's just calculate how many times we would expect to hit the bullseye if that H0 was to be true, so if the probability was 10%. If the probability was fixed at 10%, then we would expect 2 successes at hitting the bullseye out of 20, because obviously 10% of 20 is 2. Now, what I've done here, I've just drawn out a number line of the number of successes, right? So we could get no successes. If you throw a dart 20 times, you may never hit the bullseye. That would be 0 successes. But you could get 20 out of 20. Okay, so that's our number line of successes. And again, this is what we're expecting. So let's say that I threw the 20 darts and I got 4 successes, 4 bullseyes. So that's what we achieved. That's what would have been expected if the government was correct. That's what we should have got, but we got 4. Now, the question is, based on this experiment of 20 throws, who is more likely to be correct? The government or me? Now, there are 3 kind of ways that you could go about deciding who to go with. Now, if you're a statistician, your colleagues won't be happy with option 1, but option 1 is that you could just decide yourself, right? You could just decide, okay, well, 4 is bigger than 2, so I guess the H1 is more likely to be true, so I'm going to go with H1 as my conclusion. You could do that. Now, you could say, well, we've only thrown the dart 20 times, so let's be a bit more fair to the government. Let's say that if we get 7 or more successes, so 7 or more bullseyes, then we will go with my hypothesis, but if we get less than 7 bullseyes, then we will stick with the government's hypothesis. You could do it like that. So let's go with that. Let's say that 7 or more successes means that we go with my conclusion, but anything else, we go with the government's conclusion, right? So in this case, I only got 4 bullseyes. I didn't quite get 7 bullseyes, right? So I'm going to have to stick, unfortunately, with the government's H0, right? Because I chose that 7 or above was going to be the set of numbers that would make me reject H0. Now, if we're going to be technical, what I've actually just done here is I've created something called a critical region, okay? So a critical region is a set of numbers in which we would go and reject H0, right? So we go with H1, right, if we get 7 or more successes. So in other words, we reject this one here, right? So that region of numbers is called a critical region. And then all of these numbers here, 0, 1, 2, 3, 4, 5, 6, this is the acceptance region, because if you got 6, 5, 4, 3, 2, 1, 0 successes, you would have to accept H0. So this is accept H0, this is reject H0. Now let's talk about another key term that you need to be aware of. So again, the critical region, the set of numbers in this case where we reject H0. Another term you'll see is the significance level. And the term significance level just means the probability of rejecting H0. So if I said to you, work out the significance level for this scenario, what you would do is you work out the probability of getting 7 successes, 8, 9, 10, 11, 12, so on and so on, add them all together, and that would be the probability of rejecting H0. It would be your significance level. And if you've seen binomial distribution and you've calculated binomial distribution probabilities on a calculator, you'd be able to do this on your calculator to work out this probability here. Now, why was this not a very good hypothesis test? Well, because I decided what the critical region was. Okay, I decided that 7 or more successes was going to make us reject H0. I actually chose the numbers myself. That is not a very scientific or mathematical approach, just deciding what's going to be okay and what's not going to be okay. Now, there are two ways that you could make this whole situation more mathematical. Now, one way that you could deal with this is to kind of forget this idea about critical regions and significance levels. You could do something called a Bayesian inference. Now, Bayesian statistics, Bayesian inference is beyond A level, you don't need to worry about it. It's probably on average like second year university material, depending on your university. The idea is that before you collect any data, you give the two hypotheses a probability of being true. And then as you throw each dart, so in other words, as you collect an extra piece of data, you update those probabilities depending on the result of the dart. Now, to do that, you're probably looking at some very hard integration, or more likely what most people do is they use some computer coding to do it for them. But in A-level maths, this is the method you will do. Instead of me choosing the critical region, which is what I did with this example where I chose 7 or above, you're actually going to choose the significance level instead. So the idea is that you actually choose the chance of rejecting H0 before you even collect any data, because then you know without even collecting data what the chance is that you're going to go with this conclusion instead of this one. Now, to be really precise, I should say here that this is the probability of rejecting H0 given that H0 is true. That's actually really important. I'll just add that in there. Don't forget that in your exam answers, because the thing is, right, you can't calculate this probability, right, the probability of getting 7 or more successes, if you can't assume that that's true. You have to assume that's true, right? So that's just important to mention. So again, we got our number line here, right? The number of successes, we expect to get 2. I actually got 4. Let's say we have a 5% level of significance. So normally in exam questions around 5%, 1%, 10%. Now, the way that I like to explain this is a little bit naughty, because actually we've got discrete data here. Okay, so like when you throw a dart, you can't throw a decimal number of darts, okay, right? Only whole numbers. So this is discrete data, but this is the best approach that I find of explaining this. If H0 is true, we expect to get 2 successes. So I'm going to construct a new number line where I put 2 in the middle, 20 at the end, and 0 here. So 2 is my average, that is what I expect. Now, using this naughty approach, there is a 50% chance of getting between 0 and 2 bullseyes, and there is also a 50% chance of getting between 2 and 20 bullseyes, because 2 is my expected value. Now, again, because this is discrete data, this actually isn't quite true here. If it was continuous data, this would be perfect, right? So if it was like heights and times, this is a perfect explanation, but I still use this explanation even for discrete data because it just makes sense. So if we have a 5% level of significance, and if H1 was, as I said at the start, the probability of me getting a bullseye is bigger than 10%, so in other words, I expect to get more than 2 bullseyes, right? Then we're going to be focusing on the upper tail of this distribution of numbers. So basically, whatever numbers fit into this gap here, this 5% probability gap here, those numbers will be in my critical region. Now, I actually went on the calculator and calculated some of these probabilities myself, but what I found was that basically there's about a 13% chance of getting 4 or more bullseyes, but about a 4% chance roughly of getting 5 or more bullseyes. So the number 5 is going to be somewhere here in this critical region, but the 4 is not quite in that critical region. So that's telling me that the number 4 bullseyes is not enough to be in the critical region. It's not big enough, so I didn't get as many successes as I would have hoped for. So that means we have to accept H0. There is insufficient evidence that the probability of my success is bigger than 10%. More hypothesis tests are coming soon, so make sure you follow.